Hello everybody, my name is Mariescu, and today we're going to talk about shape-based route search. So, in large collections of GPS trajectories, users spend a long time looking for one trajectory that they have in mind. And this is mostly because trajectory collections are very large. They are growing all the time. People always collect these trajectories. They may not remember the exact day and time that they recorded some trajectory, and sometimes they don't even remember the year. This is, for example, if you go cycling maybe 2 years ago with a friend, you maybe don't remember if it's 2 years ago or 3 years ago. So it can be very hard to find a specific one, and trajectories are sometimes overlapping. So in example like here, you don't really see your trajectory because it may be overlapping by other trajectories there in the map. So what we propose is some real-time search for routes in trajectory collections, and this is a combination of user gestures and pattern matching. So the gesture is this kind of hand-drawn input that the user can make any kind of shape on the map, and according to this paper, you can characterize this as a symbolic type gesture, and according to the second paper, it is going to trigger a command. So our gesture is going to basically trigger a search in the database to find the trajectory that we are looking for. So it looks like this. You have the map over here, and the user is going to make this line here on the map, and after the user is drawing that kind of line, the system is searching and it's going to output a result. Here we have two trajectory results, and maybe one of them is exactly the one that the user is looking for. So user can now click on each of them and download them, or look at the properties, or do whatever they wanted to do with this trajectory in the first place. So how the algorithm works here, it is basically trajectories are not seen as lines anymore, they are seen as cells. So we have a large grid, and in this large grid we have the cells that the trajectory is going through. They are going to represent this trajectory. And if you can see here, we have this function on line 6. We have function called WJS to MGRS. So you should be familiar with this MGRS grid system, and how this WJS is transformed to that. It's quite common. And because the points are far away from each other, we use this interpolation between the points. And in the end, it is important to note that the number of cells of a trajectory is linearly dependent to the length of the trajectory in meters or kilometers or whatever the measure is. So once we have this algorithm there, we have the cells, and to make the method efficient, we use the B3 index in the database. So this B3 index is very important because it's going to make our search go in logarithm time. So if we want to find all trajectories that go through one cell, they are going to be in, all the trajectories are going to be found in logarithm time, even if the B3 is computed in the worst possible way, stored into the database. Now, it is needed that we introduce a similarity function, because when the person is making that line on the map, we want to see how similar that line is with any trajectory in the database. And we use this cell representation here to calculate a measure for similarity between two sets of cells. And this similarity function, we calculated in this algorithm. And you can notice here on the top that it is very similar to the bottom. This is because we treat the original cells of the trajectory and the dilated cells of the trajectory in the same way. The input for algorithm is also this zoom level you can see here. It is also very important. Without that, it doesn't work very well. And this get roots function from here is the one that works in the logarithm time, and you can see also here implementation on the bottom. Yes, so in the end you get some results, some trajectories, and they are sorted, so that the ones that are most similar to what the user did in the beginning are going to appear on the top, and then the less similar ones are going to be later on. So hopefully the result is going to be one of the top trajectories in this list. We wanted to see if the method is good, so we asked people to test this method and find trajectories. So we had 11 people here that they were testing the method and trying to find trajectories, and on average they are finding the trajectory in 84 seconds. But you can see here that some of the people, like 1 and 2 and 5, it is less than 1 minute. This 1 and 2 is very close to half a minute, so it's quite fast time to find the trajectory for some of the people. Some of the people are not doing that good, like this number 4, but we think that they can learn. So they just need to practice more to find the trajectories, and maybe it will become better in time. And additional findings we have that the length of the trajectory, this one here, is important observation, because it looks like people find short trajectories fast than they find long trajectories. I don't know exactly why, but it seems to be consistent. Long trajectories are harder to find. And then this complexity, if a trajectory is complex, again people find it slower than if the trajectory is simple. And important to mention here that it's not obvious, but to measure the complexity, we use this polygonal approximation method, which reduces the number of points to the minimum necessary to represent the trajectory while maintaining its shape. So the number of points in this representation varies depending on the complexity of the trajectories, which is equal to the number of turns that the trajectory is going to have. And you can learn more from this paper here if you are interested. And finally, this density. So if you have many cells in a region, that means that you have many trajectories that are overlapping each other. So if the density is high, if there are many of these, then the users find the trajectory slower. So users are better at finding the trajectory in places with not so many trajectories. In conclusion, the method is fast, so people can find them in 84 seconds on average. And the function that we showed before, you can actually compute it in linear time using this hash map. You can see it from the algorithm. And we use this B3 indexing to make the things faster on the server. Do you have any questions? Yes?
I'm not familiar with MeGRS function that you mentioned. Can you explain more?
It is it is a standard that it is used by NASA. So NASA is using this MGRS to locate places on the Earth, and you can find this implementation available in most languages.
Okay, that's
It makes cells. It makes the cells. It takes the points and it tells you where the cells is. Yes. Any other questions?
Excuse me.
Yes.
What was the first question?
I'm sorry. So the first question, it was how the cells are how you find the cells from the GPS points.
Okay. And your answer was?
We use this MGRS system that you can. It is implemented in many different languages, and you can anybody can use this library.
One question about the evaluation. You use the people to check the goodness of the algorithm.
Yes.
Is it rather subjective method?
Yes. We have made also some more objective experiments for the time it takes to find these, but you can see them in the paper. This method is aimed to be used by people. So we experimented with people.
Okay, thank you.
Any more questions? Okay, so thank you very much, and now give me grades. Okay. Hello everybody, my name is Mariescu, and today we are going to talk about a new method for searching trajectories, which to our knowledge has not been tried out before, is to search them based on their shape. Typically, large GPS trajectory collections look like this. They become similar to spaghetti, if you will, and it becomes very hard to notice one particular trajectory, for instance, this circular one that was highlighted just now. Even if you know that such a trajectory exists in the data set, you will have difficulties finding it, because if you try to highlight it by moving your mouse or finger on the map, most likely other trajectories which are overlapping it are going to appear instead. If you do happen to find it, then you're lucky and you can proceed and do whatever you want with it. But it's not an easy process to solve. What we propose is to start off with an empty map, so no need to load any trajectories in the beginning. But what the user must know is an approximate shape of the trajectory he is looking for. Once the user draws this shape, an automatic method searches the database and finds the most similar candidates from there. And after that, user can choose to download it or check out the different statistics or properties or whatever he intended to do with the trajectory in the first place. So the drawing that the user is going to do in the beginning can be seen as another trajectory. From all intended purposes, each point in the drawing has a location on the map and a timestamp when the person was drawing that shape. Of course, it's much faster than a real-life trajectory, but still it can be seen as a route. To see which one in the database is spatially similar, we employ a spatial similarity measure that is referred to here. And what it is, in fact, it's a variation of the Jacquard similarity coefficient, which works with the cell representation of trajectories and simply counts how many cells are shared by both trajectories, ones shown in red here, as a proportion of all the trajectories found in the two, of all the cells found in the two trajectories. Now, this Jacquard similarity coefficient was not good enough to give a meaningful measure, because even though it works relatively well in this example, if the grid would have just been slightly offset, the trajectories appear not to be similar anymore. So to fix this, we decided to use a slightly more complicated variant of the function, which uses also morphological dilation on the cells and basically has a buffer region when calculating the similarity. To do the search, one needs the input, which is first converted into these cells. And after that, I want to reattract attention to our similarity measure. And we can see that the similarity measure can be broken up into several different parts. The first part we will record in this structure object, in this AB variable. The second part is going to be in this ABD variable, D standing for dilated area. And ADB is going to keep track of the opposite side, so A dilated and B undilated. So how the algorithm proceeds is it first investigates all the original cells of the trajectory. So it goes through each of them. And for each cell, for example, that one, it queries using the getRoots function all the roots in the database that pass through that respective cell. And if the root itself passes through that, then we increase this counter by 1. Alternatively, if the root doesn't pass through it, but its dilated representation passes through it, we increase this other component that we also need for our similarity function. So now we have 2 of them figured out. For the other half, we need to look only at the dilated representation. And in this dilated set of cells, we will look again, for example, here to see which trajectory passes through that. And that's how we get the final component. And I want to attract attention that we don't need to look at trajectories that their dilated representation passes through the dilated region of the original trajectory, because they are not part of the original similarity function, which we found out to be more similar to what user expects as a result. Finally, we compute the final similarity by adding up the components which were previously calculated and 2 additional values that can be just retrieved from the properties of the trajectory itself. I'm using the marker. And in result, we're going to get this type of sorted list with the most similar trajectories to the input in the beginning. Now, because of this getRoots function, we typically get a complexity which is above n log n. It's actually a quadratic function depending on all the trajectories in the database, which is quite slow. However, we can index, for instance, using B-tree index the database, and then we get the function which is in terms of the logarithm of the total number of cells in the database. Now, what does this mean in practice? It means that for a database of roughly 10,000 roots, we get results in real time. Real time meaning less than 1 second. Now, the scaling of this algorithm is not that good in the sense that when more and more trajectories are going to be added into the database, this time required for getting the result is going to continue to increase, even if these trajectories are going to be added elsewhere than the user is looking at. but the increase is going to be still logarithmic, so it's not a danger in the immediate future. It's still something that should be considered. Finally, I should discuss a little bit about how the trajectories are, how the cells are computed. By that I mean, what is the size of the cells? Because this is quite important in this application. If you ask the person to draw a trajectory at this zoom level, he's going to have some error in the drawing, of course. But what is going to happen if we are going to focus on a zoomed in version at the same location? Basically, if you zoom in the map, the user's accuracy in drawing should double, because all the details on the map have doubled through the zoom-in process. So because of that, we actually record for each trajectory multiple resolution cell representations. So we have smaller cells and larger cells, and depending on the zoom level that the person is using at the moment, one of them is going to be chosen and the rest of the evaluation is going to follow. Yeah. To see how fast people are able to find their trajectories using this newly proposed method, we asked 11 volunteers, and for each of them we asked to do 10 searches each, and the search looked like this. So they were shown a trajectory on the map, and they accumulated a total of about 200 such search tasks, which lasted about over 4 hours, and with an average time of 1.2 minutes per task. The tasks that they had to choose were actually not the same. First, they were asked to find the trajectory using a traditional system. In the traditional system, you have the trajectories listed in such a list, or by using a calendar system. And in MOPSI, we also have the possibility to display them on the map. I want to add that this is actually advanced compared to other systems, which only display the start point of the trajectories on the map, which makes it harder to identify which trajectory you are looking for. But for this purpose, we use the one in MOPSI. And the gesture variant, which is proposed here, the map was empty, but the person was asked to recall how the trajectory looked like, and after he is drawing it, we'll get the list of most likely candidates. And if the result is not in that list, they were asked to do the drawing again. So it may be that they don't remember exactly how the trajectory looks like, and then the person had to do it once more. So what happened? Well, sometimes people gave up. This is not an easy task to do. It's quite hard to find a trajectory in that kind of mess. But people gave up less in the traditional approach rather than in the gesture approach. And from wasted time point of view, the gesture variant was 41% faster than the traditional approach. And if we look a little bit at the individual level, we can see that most of the times required for the traditional approach are higher. It's not always the case, but are higher than the times required by using the gesture variant. And except for one particular user here, who now I have to mention is in the group of the first 4, which were highly experienced users of the traditional variant. So all these other people didn't know any of the 2 methods before. They were just asked to find trajectories. But these 4 guys here, they were experts of the traditional variant. So what I want to stress here is that this is actually normal behavior. When you get an update to your favorite application and it's doing everything differently, you're always complaining, damn it, it was better before. But that's just because your experience from before affects the way you're using the new system. So what we got instead is that 3 out of these 4 users still found the trajectories faster with the new variant, which is a good indication that it's a good method. So now I want to attract attention to this few details. Based on the length of the trajectory, it seems like people are able to find trajectories that are shorter faster. Based on the complexity of the trajectory, it seems like people are able to find trajectories that have less complexity faster. And by complexity, we mean number of points necessary to represent the trajectory, minimum number of points necessary to represent the trajectory. So in this example, using just 10 points, it's able to get the shape of the original trajectory quite well without any noticeable loss to the user. So trajectories that require more points to be represented are harder to find using the gesture search. And finally, density. People are able to find trajectories faster if there are not many trajectories in the region. In conclusion, okay, this gesture approach seems to be faster no matter what the case. So people are able to find that trajectories quicker than the traditional one. And in conclusion, this new method is 41% faster than the best that exists to our knowledge. The query time is real time for up to 10,000 roots. And the method scales logarithmically, meaning that we don't have to worry about inventing a new method soon, but it's not going to last forever. Do you have any questions?
Yes.
Yes.
You don't have page number, so it's difficult to target at the slides. Can you tell me how you get the result, this function, how it works?
I'm sorry?
Can you go to the algorithm? Yes. You have a get results function here.
It runs.
Yes. How does it work?
Okay, so the question was, how does the getRoots function work? I don't have this information in the slides, unfortunately, but the way it works is a simple MySQL query where the ID of the cell that you are looking for is going to be the parameter. So it's a select from the table where the ID is given. I want to attract attention that the ID is known here for this one particular cell. And in this for loop, we are going to ask this getRoots function for all the cells in the representation. So the function is actually just a MySQL query, where you find all the trajectory IDs that have a cell ID in their composition.
So if yes, then it means this row pass through the...
Yes, this is one example that will be returned when the getRoots function is called.
So by query the sales ID, right?
Yes, query by cell ID. Okay, any other question?
About the user...
Sorry, I have another question from the lady behind. Yes?
I think you mentioned like your trajectory many times.
Can you repeat?
I think you have mentioned the trajectory many times.
Trajectory many times?
Yes, but in the slides it shows like a root.
Oh, yes. Okay. So the question was, I have mentioned the word trajectory many times, and in the slides we have this word root. I have to say that they are equivalent in this presentation. So in this presentation, I'm sorry if I said the word trajectory instead of route. I meant the same thing. Unfortunately, this presentation and this paper was written with my colleague, and we can't decide what is the proper term to use. So apparently part of the slides are using his terminology, and my off the bat word here is trajectory. But I'm sorry about that. Any more questions? Yes?
Yeah, I thought to ask the same question like before this presentation, but because there was some kind of comparing to the traditional now methods and these new methods, I guess I just believe it. But you can answer if you want to. The question was that is this suitable evaluation to these results?
You mean the human evaluation?
Yeah.
I think so. Again, I'm going to reply the same that it was before. So the question is the evaluation suitable only from the human perspective? So in the paper, we do much more evaluation there, but the results are very obvious. I mean, based on the analysis of the complexity functions, the results are matching to that fairly well. So there was nothing surprising. In this presentation, we decided to report just the more noticeable, more notable results. So from objective point of view, things seem to follow the complexity function fairly well, so we didn't report the objective experiments in this presentation.
Okay, thank you.
Yes. Okay, and finally I have to say something about Mingyue. So in practice today, so for a long time people were saying route or trajectory all the time, but more recently, like in the last 5 years or so, people are now claiming that route is something that is clearly defined. For example, you have a cycling route, but why do you have a cycling route? You have a cycling route because several people have decided to go cycling on the same area again and again. So basically the route just means this one representative trajectory for that set of different trajectories. But we have started to use also this term recently, so it can be a bit confusing. This was introduced mostly by sports trackers. I think Runtastic sports tracker was the first to introduce this term officially. But they refer to trajectories separately as traces. So people name things differently, so you should define the things always when you give one presentation, and I didn't do that. Okay, but now how about the grades? Yes, okay, one more.
If I get the presentation right, I think the user has to have some kind of knowledge about the trajectory,
Yes.
the visual knowledge.
Yes.
So how, if the user does not have any kind of visual knowledge, how effective would this
It will not work. He will not use this. So the question is, what if the user doesn't remember what the trajectory looks like? It's not going to work. But then I have the question, how are you going to even find it if you don't know how it looks like with any method? Because if you think about it, let's say, so this is now my last month's trajectories, and the way I recognize one trajectory, of course I could go one by one in this list, so linear search through all these 16 different results. But how do I know I found it if I don't know how it looks like? So if I know how it looks like, for instance, this red line here, then I can probably draw at least a similar result as the one that I remember. So I don't have to remember it specifically. That's why the method outputs several most similar candidates, and probably one of them is going to be in the results. But if you don't know how it looks like, you can only look at the time and the speed, and it's hard to identify a route based on those properties. So this is the most likely way to identify a trajectory. Okay, how about we move to the evaluation?